welcome. My name is Ashish Ahuja. I'm an applications engineer with Texas Instruments. I'm really excited to introduce you to the brand new Tiva C-Series TM4C129X family of microcontrollers for applications that connect, communicate, and control. In this video, we will briefly talk about the clock control and configuration on TM4C129X devices. But before we talk about that, I want to mention that the TM4C129X microcontrollers are built on TI's proprietary 65nm technology. They feature prolific connectivity peripherals such as integrated Ethernet MAC and PHY, USB on-the-go host device, CAN, I2C, SPI, etc. that allow for connectivity, communication, and control over a variety of interfaces. The seamless integration of these features along with sophisticated analog peripherals and a floating point ARM Cortex M4 core provides a scalable and cost-effective solution to a large number of home, building, industrial, automation and control applications. Alright, so by the end of this video, you will be well versed with the fundamental clock sources on TM4C129X family of microcontrollers, and you will know how to configure the main system clock on TM4C129X devices. We will together compare different clock sources and briefly talk about clocking for different peripherals also. So let's get started. Several clock sources are available in the TM4C129X devices. There is a main oscillator, precision internal oscillator, low frequency internal oscillator, real-time clock oscillator, and a hibernation low frequency oscillator. Each of these clock sources is unique in the terms of its clock generation capability, that is the frequency range and precision. Let us take a look at each of these clock sources in detail and compare their capabilities. The precision internal oscillator can provide a 16 MHz clock with 1% precision. It is enabled by default upon power up, and it can be used to generate system clock as well as drive the PLL. It is typically used in applications where connecting an external crystal may not be required due to cost concerns. Then we have a main oscillator, which can be used to generate system clock with frequencies up to 120 MHz using an external crystal or using a single lead-in clock source and a PLL. It is disabled upon power on reset, and it can drive a PLL. In order to clock the peripherals at a much slower clock rate in order to reduce overall power consumption, a low-frequency internal oscillator is also available. It is enabled by default on power on reset. Keep in mind that it cannot drive the PLL, but it can generate a usable system clock. In order to clock the hibernation module and to generate the clock for the RTC, the hibernation module features a hibernation low-frequency oscillator and an RTC oscillator. They are both disabled upon power on reset and are typically used in deep sleep or hibernation mode. And lastly, there is a PLL which gets its clock from the main oscillator and can be used to generate system clock frequencies up to 120 MHz. Now that we have discussed each of the clock sources in detail, it's time to learn how to configure the system clock. We have developed peripheral driver library as a part of TivaWare for C-Series, which contains system clock control APIs to configure the clock sources. The API is called syscontrol clock frequency set. It is a new API and it replaces the older API, syscontrol clock set, which can only be used with TM4C123X devices. System control clock frequency API returns actual configured system clock frequency by API in Hertz, or 0 if the value could not be changed due to a parameter error or PLL lock failure. It takes the requested processor frequency in Hertz as one of its arguments and configuration of oscillator source and system clock source. An example to configure the system clock to be 40 MHz is shown on the screen. Pause here for a moment and take a look at it. Please note that the syscontrol clockget API is not available on TM4C129X devices. It is only available on TM4C123X devices. The clock to other key peripherals can also be obtained from different clock sources. For example, ADC clock can be sourced from main PLL or precision internal oscillator and main oscillator. Keep in mind, however, that the system clock must be at least 16 MHz while using the ADC. Likewise, the system clock must be at least 30 MHz while using the USB module. Another important point to note is that the system clock must be at least 20 MHz while using Ethernet MAC. If you are using integrated PHY, please make sure that you have a 25 MHz clock source connected to the main oscillator. The clocking mechanism on TM4C129X devices has been designed while keeping your end application in mind. The new clock distribution tree provides clock to most peripherals from a single clock source. Let me explain this further. Take a look at the illustration on the screen. Only one single 25 MHz crystal can provide clock to Ethernet module and the main oscillator. Hibernation module can be clocked internally from the hibernation low frequency oscillator. This results in reduced BOM cost and PCB footprint. Comparing this with the TM4C123X devices, separate crystals are required to generate system clock and hibernation clock. The clock control provides significant benefit when compared with the legacy devices where 3 separate crystals were required. Before we conclude our discussion, I would like to quickly educate you about the main PLL also. As I mentioned before, PLL is used to generate system clock from either precision internal oscillator or main oscillator. It can be configured to operate in normal mode and powered on mode. It can be shut down during the deep sleep mode to reduce the overall power consumption. Equations to calculate the output frequency of PLL are shown on the screen. Just in case if you're interested, take a look at it. So today in this video, we talked about the fundamental clock sources on TM4C129X family of microcontrollers and learned how to configure the main system clock on TM4C129X devices. We compared different clock sources and briefly discussed clocking requirements for different peripherals. Should you need more information, please follow the links on the following screen. Keep innovating and have fun. See ya.